Welcome to the Deep Dive, the place where we take stacks of knowledge, sometimes separated by decades, and give you the fundamental insights you need to be instantly fluent in a subject. If you have ever used a software application or even just saved a file, you have benefited from the long, sometimes painful evolution of the developer's toolkit.
That's absolutely right. Today, we are undertaking a really fascinating historical and technological deep dive. This isn't just about listing new tools. It's about understanding the core physics, the feel of coding. We're tracking the evolution of the basic tools, the source control systems, the editors, the testing frameworks, from the absolute stone age of computing in the 1970s right up through the radical workflow-shattering shifts of the late 2000s. I'm talking about things like the introduction of Git and these incredibly powerful IDEs.
And our mission today is pretty straightforward. We're diving into practitioner sources that span this entire history. We want to understand how fundamental concepts like how do you save a file or how do you collaborate with a colleague without, completely destroying their work? How have those things changed? And maybe more importantly, why do today's highly automated systems feel so vastly different from their predecessors? We are looking for the profound shift in the developer's mindset that comes with, technological liberation.
And what you'll see is this powerful paradox. The constraints of the past, the ones imposed by slow physical hardware, they actually enforced a really rigid level of discipline. Today's systems, with all their speed and freedom, they demand that we voluntarily impose that same level of discipline,
Right.
just, in digital form.
Okay, let's unpack this. We're starting with the ultimate low-tech environment. To truly appreciate what we have today, we have to go all the way back to the Bronze Age of coding, development in the 1970s.
Yeah, we have a superb anecdote from 1978. It details work on a telephone test system. The total source code size was approximately 80 KSLOC, so 80,000 lines of source code, which, might be an average file on your laptop today, but back then that was a significant, sprawling project.
Right.
But the defining constraint of the era wasn't the code size, it was the storage medium.
It was kept on tapes, specifically magnetic tape cartridges, which the sources compared to the old 8-track stereo cartridges. Endless loops of magnetic material.
Right, and this brings us immediately to what I'd call the tyranny of the tape drive. The absolute defining characteristic of this entire development environment was the movement constraint. Just think about the physical mechanism of a tape. It could only move in one direction forward.
That sounds utterly debilitating to modern ears. So if you were searching for a specific file, say file C, and the drive was at the start of file A, you had no choice but to skip over A and B until you found C.
Exactly.
And if you realized you missed something back in file A,
You couldn't just quickly reverse? Nope. You had to initiate a full rewind.
Wow.
All the way back to the very beginning, what they called the load point. The physical limitations of the hardware dictated every single aspect of the coding workflow.
the sources even mentioned how the size of these cartridges, 10 feet, 25 feet, 50 feet, 100 feet, that was a strategic choice.
It wasn't about storage capacity, not really. It was about minimizing downtime. That's the critical insight. The longer the tape, the longer the penalty for having to reset. The source material specifies that a 100-foot tape took 5 full minutes just to rewind to the load point.
5 minutes.
5 minutes of absolute non-productive downtime. You're just sitting there waiting for metal and plastic to cycle.
I can barely wait 5 seconds for a page to load today. That staggering penalty imposed every single time you needed to correct a path or start an operation over. It must have forced an unimaginable level of mindfulness.
Oh, absolutely. And the stress was just inherent in the system's fragility. Errors were common. Read and write errors would just happen because the tape was old or dirty or maybe just slightly misaligned. If a read error occurred, you couldn't rely on the hardware to handle it gracefully. You had to wind the tape all the way back to the load point and start the entire read operation again. Consuming another 5 minutes? Maybe. Maybe. Only to fail again halfway through.
And this necessitated manual physical redundancy.
Yes. The source code tapes were always written in pairs. Always. If the primary copy went bad, the whole multi-step process had to restart using the backup copy. This was the only way to manage critical failure. It was a kind of primitive, enforced backup routine that relied on the developer's discipline, not some automated tool.
So let's look at file management under these constraints. How did they even navigate the code base?
Well, the tapes were segmented into files, but there was no digital index they could easily query, nothing like that. Finding a file meant loading the tape and skipping files one by one, until you reached the position you wanted. And to do this, they had to maintain a physical listing, a paper directory of the source code, kept on a shelf.
So you literally had to consult a paper printout to know, okay, the file I need is file number 17, so I need to hit the skip command 16 times on the tape drive. That's preparation for the sake of survival.
It is. And the process for editing was equally meticulous. They maintained a master 100-foot copy of the source code stored safely on a shelf. To edit one small section, you would load the master, seep to the required file, and copy only that file onto a much shorter scratch tape, maybe 10 or 25 feet.
Specifically to minimize the time the master tape was even in the drive, exposed to the mechanism.
Exactly. And then the master tape would be rewound and put right back on the shelf. Your entire editing session took place on that temporary scratch tape.
And the editor itself, that the sources mentioned, was actually pretty good.
It was. The editor, ED402, was praised by the source. They said it was very effective, similar in feel to the enduring Vi editor. But even with a good editor, the tape constraint just defined the experience. You would read a page of code, maybe 50 lines, from the tape, edit it, write the new page out, and then read the next page.
And here is the most critical constraint, the one that, to me, speaks directly to developer psychology. Once you wrote that edited page, you could not look back at what you had just done, and you could not look ahead to what was coming.
That lack of real-time context is what forced extreme pre-planning. You couldn't rely on the screen to maintain your context. Developers relied entirely on physical paper listings, marking up changes, and planning the entire edit sequence on paper before they ever loaded the tape into the drive.
The sources explicitly state that trying to edit code directly at the terminal without referencing those physical listings was considered suicide.
It was just too risky. You'd get lost. You'd make a mistake.
What?
That physical constraint enforced planning and discipline that, frankly, we rarely see enforced by modern tools. The planning had to happen before the fingers even touched the keyboard.
It really creates a foundational understanding. In the 1970s, the developer's time was cheap, but the machine's time and the tape's integrity, that was expensive. All discipline was geared toward minimizing machine downtime.
Right?
That sets the perfect stage for our next topic. So they've done the edits on the scratch tape. Now they have to somehow integrate those changes back into the masters. But how do they manage concurrency? How do they stop two developers from editing the same file at the same time and creating a conflict?
This is the genius and the absurdity of the Bronze Age solution.
Yeah.
We move now into the revolution in source code control, starting with a system of physical, manual, pessimistic locking.
Here's where it gets really interesting. Software concurrency managed by physical office supplies.
This is pessimistic locking made manifest. It's beautiful, in a way. The system, noted in the sources from the late 70s and early 80s, was managed by a bulletin board and a set of colored pins.
The sources mention the 3 developers, each with their own color, and the bulletin board listed all the different code files or modules.
And if you needed to edit a file, you physically went to the bulletin board and you placed your colored pin next to that file name. That act was the lock, and the rule was inviolable. If a pin was in a file, you could not edit it, period.
It's a charming system, but it sounds like a workflow catastrophe. I mean, what if a developer locks a critical file and then gets pulled into an all-day meeting, or just forgets to take the pin out before they go home?
Everyone else is simply paralyzed. That was the nightmare. Pessimistic locking enforced strict serialization. If a file was locked for a day or two, everyone who needed to work on that system was stuck. It created massive bottlenecks, and it necessitated constant face-to-face communication just to manage access rights. You'd have to go find the person and ask them to move their pin.
So as we transition through the 80s and 90s, the industry fundamentally shifts away from that model to optimistic locking. The era of the pin system is mercifully over.
This shift represents a psychological breakthrough. It really does. Optimistic locking essentially says, we trust you to work concurrently, and we will deal with the conflicts later. So instead of checking out tiny individual files, developers began checking out the entire system. And crucially, the tools became incredibly sophisticated at resolving those concurrent changes.
And the mechanism for this sophistication is often misunderstood. It's not just comparing the new file with the old one, is it?
No, not at all. That's the key. The power of modern merging tools lies in the 3-way comparison. The tool analyzes the changes you made, the changes the repository received from others, and critically, the common ancestor of those 2 files. By having that shared history point, the tool can accurately figure out which changes belong where, automatically integrating most concurrent edits without any human intervention.
So the system is smart enough to figure out the integration puzzle. You just keep working, and the tool manages the complexity of all these parallel development streams.
That's the high-level benefit, yes. The process does require an update operation before you can commit your code. You pull in others' changes. The tool attempts at automatic merge. You resolve any remaining conflicts, which the tool flags very clearly for you, and then you commit the merged clean code. This is what allows for high velocity and high concurrency.
This transition leads us to the centralized version control systems that reigned supreme for a long, long time. CVS and Subversion, or SVN. While CVS is pretty much obsolete, SVN is still out there. It's a solid centralized system.
They worked well for that basic update, merge, and commit loop, but the sources highlight a cultural problem they fostered, which they term branching austerity.
Tell us more about that. Why was branching seen as such a burden in the SVN era?
Well, because the tools were centralized and managed, merging less elegantly than modern systems do. Branches were often just avoided or heavily restricted by management policy. Merging a branch back into the main line, especially a long-lived branch, was often a difficult, manual, painful process. You had to track exactly what changes were going in, manually verify complex file conflicts, and often the process itself was just slow and error-prone.
So management would typically mandate that if you created a branch, it had to be a short-lived feature branch. You had to merge it back into the main line before the sprint ended, just to minimize that integration risk. The cost of technical reconciliation was just too high.
Exactly. And that high cost is precisely why Git, introduced around late 2008, was a genuine seismic shift in developer culture. Git is the undisputed leader in distributed source control systems today.
The core concept of Git is the mind bender you mentioned earlier, the complete lack of a single true mainline or central authority.
That architectural change is the source of all its power. Every developer keeps their own copy of the entire history of the project, locally, on their own machine. When you commit, you are committing to your private, local repository. The push operation is merely synchronizing your history with a designated remote, which may or may not be the main hub for everyone else.
And this distribution of history fundamentally changed the workflow. It made short-lived branches obvious and most convenient. Suddenly, merging work with each other could happen, as the source says, on a whim.
And we see this contrast beautifully illustrated in the sources. They show revision history figures. The SVN history is typically a straight line, just one commit after another, reflecting that austere, non-branching policy. The Git history, by contrast, is a complex, beautiful web, a constant entanglement of short-lived branches merging constantly.
That web is the visual manifestation of a relaxed, highly concurrent development style. Developers aren't afraid of branching for every little feature or fix or experiment because the tool handles the resulting complexity so elegantly and so quickly.
Right, but this is where we need to introduce a bit of a challenge. While Git provides this incredible freedom, doesn't distributing the history and encouraging constant merging just move the integration debt from the main server to the developer's desk? Doesn't the developer now spend more time pulling, resolving, and pushing all these local branches, potentially slowing down their own local environment?
That's a sharp point. You're suggesting the tool has made branching cheap, but perhaps it hasn't eliminated the cognitive load of integration, it's just relocated it.
It has reduced the cost of integration exponentially, due to the speed in that three-way merge algorithm. But the developer now holds the responsibility for maintaining a clean, integrated local history. The trade-off is freedom for personal responsibility. If you're disciplined, you gain massive velocity. If you are not, you can quickly generate these complex merge issues that can still be very painful to untangle. Git values local history and distributed merging, and it just fundamentally changed what developers expect from source control.
So we've moved from 5 minutes of waiting for a tape to rewind to having the entire project history locally accessible and mergeable in seconds. Now let's look at the actual environment where the coding happens, the editor and the workstation.
Well, despite the staggering technological leaps, one simple editor has demonstrated remarkable staying power.
It seems counterintuitive, doesn't it, that a command line editor from that era retains significant resurgence in popularity in the age of graphical interfaces.
Its enduring appeal is its sheer simplicity, its ease of use, speed, and flexibility, particularly for experienced developers who internalize its command structure. While modern IDEs far outclass it in features, Vi remains incredibly fast and powerful for quick edits, especially when you're operating in remote server environments where a heavyweight graphical application is just impossible. It's an efficient workhorse. Though the author does note their own use of Vi has dramatically decreased over the last decade in favor of more powerful tools.
And then there's Emacs, the other historic giant.
Emacs is a world unto itself. It has an internal Lisp model, which allows it to be completely customized and extended. That virtually guarantees its relevance for decades to come, independent of whatever language or platform happens to be dominant at the time.
But the core function of the editing environment has fundamentally changed. The sources recall a time in the 90s when point-and-click editors were viewed with suspicion, considered laughable toys. Now, we rely on these sophisticated integrated development environments, IDEs like IntelliJ.
The author's current choice, IntelliJ, is a powerful example. It supports a huge spectrum of modern languages: Java, Ruby, Clojure, Scala, JavaScript, you name it. But the key shift here is philosophical. Modern IDEs are no longer about typing lines and characters. They are about complex code manipulation.
This is a critical distinction. It really elevates the programmer's role. Can you walk us through what that manipulation looks like in practice?
Sure. Think about refactoring tools. Before IDEs, if you wanted to rename a variable that appeared across 50 files, there was a painstaking manual and incredibly error-prone process. You were almost guaranteed to miss a usage or misspell something. Now, with a single command, the IDE renames that variable globally, safely, and instantly because it understands the code's abstract syntax tree. It sees the code as logical structure, not just a wall of text.
Or take a more complex example, like extracting a superclass. That used to involve hours of copying logic, identifying shared interfaces, adjusting inheritance, and then testing all the results.
Exactly. The IDE can now perform that kind of complex architectural transformation in seconds. Other examples are extracting methods, moving logic from inheritance to composition, or safely converting a loop structure. The IDE lowers the cost of change dramatically.
That is profound. By making these improvements cheap and safe, the IDE fundamentally changes how you manage technical debt. You're no longer afraid to restructure complex code because the tool can perform the surgical transformation for you instantly.
The programming model has moved from meticulous typing to high-level transformation. Developers spend less time focused on the next character and more time focused on the next few transformations needed to make the code base cleaner, better structured, or more abstract. You are modeling the system through continuous improvement, not just constructing it from scratch.
So the IDE elevates the programmer from being a meticulous, detail-oriented typist who fears large-scale changes to a high-level architect who can instantly enact structural improvements.
Yes. But the caveat, as the sources note, is that this power comes at a cost. These IDEs, IntelliJ, Eclipse, they have a high learning curve. They require significant time investment to master the deep features. And they are resource intensive. They are not lightweight by any stretch.
Which is why there's still a niche for a powerful but lightweight alternative when all that heavy manipulation isn't necessary.
That's where TextMate comes in. It's cited as powerful and intuitive, ideal for smaller projects or quick edits, where booting up a massive, resource-intensive IDE would be total overkill. It balances speed and utility, though it lacks the deep structural manipulation features of the heavyweight tools.
Okay, so we've established how we write the code with speed and power, but a high-velocity development team creates complexity fast. This increased speed necessitates better management tools. Let's look at managing the process, tracking issues, and ensuring the code always works.
We move now to issue tracking systems. Today we have these elegant digital solutions that integrate with agile methodologies.
Pivotal Tracker is mentioned as a preference for its elegance and simplicity, fitting that iterative, short-cycle approach really well.
For smaller projects, Lighthouse is cited as being very quick and easy to set up. And for highly collaborative internal projects, many teams just rely on wikis because they offer maximum flexibility and are easy for non-developers to understand and contribute to.
But the most crucial recommendation, and this echoes the discipline of the 1970s, is philosophical. The sources strongly advise that teams, especially agile teams, should start with the manual bulletin board system using physical cards. To do, in progress, and done.
This is the low-tech precursor to Kanban. And the mastery of that manual system, understanding how to prioritize, how to limit work in progress, how to communicate status using physical constraints, that's the prerequisite. It informs the team what they truly need before they go out and purchase and configure a complex digital tool.
This philosophy of keeping the project manageable leads to a surprisingly firm stance on bug counts.
It's one of the most important takeaways from this section, I think. The sources state clearly that for a reasonably sized team, say 5 to 12 developers, the total list of active issues, tasks, and bugs should be in the dozens to hundreds.
Not thousands. If a team has thousands of bugs or features queued up, the process is fundamentally broken.
And this is where we need to dig into the why. Because if the issue list exceeds a few hundred, the word tracking loses all meaning. It just becomes an issue dump. The consequence of an issue dump isn't just a long list. It's a failure of prioritization and a complete erosion of trust.
How does it erode trust?
Well, when the list is thousands of items long, stakeholders and team members know intuitively that 90% of those items will never be worked on. Priority becomes guesswork. Estimations become useless because the scope is functionally infinite, and that feeling of being overwhelmed leads to developers ignoring the system entirely. The list ceases to be a functional guide, and it becomes a repository of historical neglect. A manageable list is essential for maintaining velocity and psychological safety.
A compelling argument for radical backlog hygiene. Okay, let's move to the project heartbeat. Continuous build, or CI.
Jenkins is cited as an excellent, simple, and lightweight tool for CI. The core philosophy here is non-negotiable. Continuous build must be hooked up to source code control.
Meaning that the moment anyone commits code, the system must automatically build the project, run the tests, and report the status immediately to the entire team.
And this leads to the modern version of 1970s discipline, the stop the presses rule. The team must keep the build green at all times. A build failure is a catastrophic emergency that requires immediate resolution. Failure cannot be allowed to persist for a day or even a few hours.
This is the modern equivalent of the 5-minute rewind penalty. Back then, the cost of error was physical time waste. Today, the cost of a broken CI is integration debt, lost trust in the system, and a deceleration of the entire team's velocity.
Precisely. To reinforce this discipline, the sources mention that in the FitNesse project, developers run the continuous build script before they commit. It takes less than 5 minutes, which is non-onerous, but it ensures changes are clean before they ever touch the shared repository. It's developer pre-planning enforced by a script, not by a physical tape drive.
This commitment to constant vigilance naturally leads us directly into the quality gate itself, testing tools.
Unit testing is foundational. And while every modern language has its specific tools, Unit for Java, Unit for .NET, RSpec for Ruby, Midge for Clojure, CPP-DESes for C++, all effective unit testing tools must share 5 non-negotiable features.
Okay, let's break down these 5 features because they illustrate how modern tooling imposes that necessary discipline. Feature 1. Speed and ease of use.
Running tests must be trivial. It has to be. Whether it's a quick command line instruction or a button in the IDE, the gesture to run tests must be instinctive. If running the test takes effort, developers will just stop doing it frequently.
Feature 2. Clear pass-fail indication.
You need an unambiguous signal. The classic example is the graphical green bar. Green means success, anything else is failure. You should never be required to compare 2 output files or wade through verbose logs to figure out if your code works. If you do, the tool has failed.
Feature 3. Progress indication.
The tool should show that work is being done. A moving graphical meter or even a simple string of dots confirms that the tests are executing and haven't just stalled somewhere. This provides crucial psychological feedback.
And feature 4 is arguably the most critical and often misunderstood requirement for maintainability, isolation.
This is where we see the tool enforcing deep structural integrity. The tool must actively discourage communication between test cases. The preferred method is running each test method using a new, clean instance of the test class.
Why is that isolation so critically important? Why can't tests share data?
Because sharing data or relying on side effects creates what the source calls a deep trap. If test A sets up a specific database state and test B relies on that state, then test B will only pass if it's run after test A. If test A fails, test B fails. Or if test B is run independently, it fails. This means tests run on their own are unreliable, and tests can only be run in a single predetermined sequence.
Which means you've lost the freedom to run small subsets of tests quickly. And if one test fails, you don't know if the failure is genuinely in the code under test or just in the preceding test case.
Exactly. The suite becomes fragile, slow, and non-deterministic. It's a nightmare to maintain. Isolation is the modern tool's way of enforcing the discipline that prevents this state dependency, ensuring that the test results are reliable and trustworthy regardless of sequence.
And finally, feature 5, a convenient API for making assertions.
The tool needs to make it very easy to verify expected outcomes. Your assert equals, assert true, things like that. If the assertion syntax is complex, developers will write fewer tests, or they'll write assertions that are difficult to debug when they fail. Good tooling simplifies error handling and setup, allowing the developer to focus purely on the logic being tested.
Moving beyond unit tests, which verify small pieces of code, we look at component testing. This operates the API level, ensuring the component's behavior matches the broader business specification.
And this level of testing is the key to unambiguously defining done. The ideal scenario is when business analysts, BAs, and quality assurance specialists, QA, collaborate to create a specification that is itself executable as a passing test suite.
So when the BA signs off on the specification, and that specification passes when run against the code, the definition of done becomes objective and measurable. All tests pass.
Right. And the preferred tool cited for component testing is FitNesse, which, full disclosure, the author was a primary committer on.
FitNesse is described as a wiki-based system. How does a wiki translate into an executable test suite for business specifications?
It allows BAs and QA specialists to write tests in a simple tabular format, often referred to as a Parnas table style, directly in the wiki. This wiki content is then read by the FitNesse engine, which uses what are called test fixtures, small code modules, to translate the table entries into calls to the system's API, executing the business logic.
So the business users are writing the acceptance criteria in a format they understand a table, and the system translates that directly into code execution.
Correct. And FitNesse is highly versatile. It supports nearly every major language: Java, C#, C++, Python, Ruby, because its execution engine, Slim, the preferred one, sits separately and communicates with the language being tested. This allows for high visibility and collaboration around those acceptance criteria.
We should also mention the other approaches. There's RobotFX, developed by Nokia engineers, which uses a similar tabular format but relies on flat files prepared with tools like Excel, and of course the behavior-driven development, or BDD, frameworks.
Yes, the BBD approach is highly popular. It was popularized by tools like Cucumber and JBehave. These tools use a plain text format driven by an engine, often Ruby for Cucumber, Java for JBehave, and they focus on the popular given when then style for describing behaviors. That narrative style is also highly successful in bridging the gap between business intent and executable code.
Finally, we have to touch on integration testing, which is often confused with component testing.
Integration tests verify that different large components, perhaps residing on different servers, all work together. They're essential, but the sources issue a very strong caution against one specific implementation: driving tests through the user interface, the UI.
Why the warning against UI testing? It seems so intuitive to test the system exactly as the user sees it.
Because UIs are notoriously volatile. They change constantly. Buttons move, labels change, CSS classes are updated for a redesign. This makes tests driven through the UI inherently fragile. These tests are prone to breaking for reasons entirely unrelated to a functional bug in the underlying business logic. This leads to flaky tests that waste valuable developer time just trying to figure out why they failed this time.
So the recommendation is to test functionality at the lowest possible level unit or component to maximize stability, and only use those fragile UI tests when you absolutely have to.
Precisely. You need a small set of end-to-end UI tests to ensure the entire assembled system works, but you should minimize their number. And for those necessary UI tests, tools like Selenium and Water are cited as the industry standards.
We've journeyed from the physical constraints of the 1970s tape drive through the source control revolution of the 2000s and into the sophisticated systems that manage code quality and project flow. Now, let's pivot to a conceptual failure that highlights what programming is really about.
This is perhaps the most compelling philosophical insight from the source material. I'm talking about the failed dream of abstraction. Specifically, the failure of model-driven architecture.
In the early 90s, there was this incredible hope centered around case tools and UML MDA. The idea was almost utopian to escape the messy details of textual code.
The grand vision was that architects would create entire systems using the unified modeling language, UML, so class diagrams, sequence diagrams, state machines, and then tools would automatically transform those high-level diagrams into complete executable source code.
This was supposed to eliminate the need for detailed line-by-line coding. It operated on the central assumption that the problem in programming was the code itself.
But the sources state plainly, the hope failed. Attempts to use UML MDA to generate large executable code bases have met with, and I quote, abject failure. Nobody truly uses these tools to generate production-ready systems from diagrams alone.
And the failure hinges on a simple truth. MDA operated on a false premise. The problem in programming has never been the code. The problem is detail.
Programmers are fundamentally detail managers. That is their core job. They must specify system behavior at the most minute, granular level. The reason textual languages code have persisted is because they are remarkably convenient for managing indexing, and manipulating vast amounts of specific, irreducible detail.
And nothing hammers this point home quite like the powerful anecdote provided in the source about line endings. This shows why even the smallest, most invisible details matter and why we can never truly abstract away from them. You mentioned the difference between R carriage return, N line feed, and the combinations that are N. Can you walk us through why this still haunts modern programmers?
Certainly. This is low-level history that has massive modern consequences. Back in the 1960s and 70s, the common terminal was the ASR33 teletype. To visually advance the paper and reset the printing mechanism, you needed two separate mechanical commands: a carriage return to move the print head back to the left margin, and a line feed to advance the paper to the next line. Hence, the sequence was established as the end-of-line marker.
But the UNIX system, seeing this as unnecessary baggage, shortened the end-of-line sequence to just N.
Exactly. They saw no need for the physical carriage return command. Other operating systems, specifically DOS and then Windows, continued to adhere to the historic RGAN convention.
Now, in the modern world, what happens when a program that expects one convention encounters the other?
Complexity, chaos, and failure. If a script expects a Windows-style R and it sees the UNIX-style N, it might fail to recognize the end of a line, or it might improperly process blank lines. Conversely, if a UNIX script reads a file with R, it might see that invisible R character as part of the text, causing word wrap failures or strange, inexplicable crashes in tools.
So, even though we are writing Java or Python code, running on complex virtual machines or interpreters, we are still constantly battling a single invisible character difference that dates back to mechanical teletypes.
That is the profound realization. Identical source files will generate different checkzones because of varying line endings. Build systems fail. Tools misinterpret input. It demonstrates that the level of abstraction provided by modern Java is not far enough above the complexity of assembly code to eliminate these fundamental implementation details. The difference in abstraction is minimal when you hit the metal.
The hope that diagrams would eliminate the need for detail failed because diagrams themselves are a language. They introduce their own details, their own grammar, syntax, and complexities that programmers must manage.
The MDA movement was a hope that detail could be wished away. But the source concludes that ultimately, programmers will need to draw code and manage that detail, just as they needed to write code and manage the detail. The complexity cannot be eliminated, only shifted.
That brings us to our final summary, reflecting on the vast progress made and the challenges that remain.
Software tools have become exponentially more powerful and plentiful. The productivity gap between today's systems and that 1970s tape-based system is just vast.
If we condense our findings, the modern simplified toolkit reflecting the source's practitioner preferences is highly streamlined. Git for source code control, a tracker system like Pivotal or Lighthouse for issue management, Jenkins for continuous build, a powerful IDE like IntelliJ, XUnit for unit testing, and FitNesse for component testing.
We've traded physical constraints for digital freedom. We've replaced the physical pin with sophisticated three-way merging algorithms, and we've eliminated that 5-minute rewind penalty. We now have tools that facilitate high concurrency and provide immediate, trusted quality feedback.
But the evolution shows that while the painful, visible constraints have disappeared, the fundamental challenge remains the programmer's core job. Managing vast amounts of minute detail, whether it's line endings, concurrent merges, or ensuring test isolation.
And that leads us to our final provocative thought for you to consider. In the 1970s, the developer was forced into discipline, meticulous planning, and serialization by the constraints of the tape drive and the pin board. Today, distributed source control systems like Git allow us incredible, unfettered freedom to check in interim builds and push releases on a whim, knowing the tool will likely handle the merge. What does that technological freedom mean for developer responsibility and code stability? And how must the developer's mindset shift to voluntarily impose the discipline that the hardware once demanded?
The ultimate tool, it seems, is not the IDE or Git, but the discipline of the developer wielding them.